Dar uma introdução? Yeah. Hi, everyone. Hi. Okay. Hi there. So, here's for another Priberam lunch seminar. Today we have Jean Alves. She's a research scientist, a senior research scientist at Feedzai, and she's going to tell us about a work of learning to defer.
Yeah.
And thanks a lot, Jean. The floor is yours.
Thank you very much. So today I'm going to talk about cost-sensitive learning to defer to multiple experts, which you probably have read multiple times already, and doesn't mean a lot now. But let's start with the overriding theme of the presentation, which is how we can apply machine learning safely in high-stakes applications. So, as we all know, in a variety of high-stakes use cases, we have adopted machine learning algorithms to varying extents. And in some cases, for example, analysis of eye scans in medicine, we already get higher performance than average with a machine learning model when comparing to even highly experienced ophthalmologists. But there are some people that instead of looking at that and thinking that we're all going to be out of a job soon, we might as well try to incorporate human decision-making and model decision-making together. So the key idea here is to take advantage of the strengths and mitigate the weaknesses of both machine learning models and human experts. So while machine learning models can, for example, surpass average accuracy when compared to a human expert, for more difficult cases or uncommon cases or out of distribution instances, it may be the case that, oh, the screen is doing something. It may be the case that for some instances, even though the model is better on average, we would benefit from passing that case on to a human expert. However, that's something that we'll have to do very sparsely because humans have a fraction of the throughput of machine learning models. And we also have to deal with the fact that human decision-making is not fully predictable. So if we have a machine learning model, we define the threshold, whatever the score means, we know what the decision is going to be based on the score. For a human, the human can make a different decision when presented with the same case on two different days. Maybe the person has an headache, maybe the person was just distracted. It's something that happens. So what can we do to incorporate these two sets of expertise into one system? This learning to defer paradigm, which started around 2022, if I'm not mistaken, argues that we should try to train an assigner, which right now is a magic box, we'll get into it, that intelligently decides based on the information we're given about an instance, so let's say just the features, if it's best to allow the machine learning model to make the final decision on that, or whether the decision should be passed along to a human expert. So the idea here is that if we do this efficiently enough, we might even achieve higher performance than the model or the human on their own. So if you imagine the human is 100% accurate on a region of the feature space and the model is 100% accurate on another region of the feature space, if we train an assigner to distinguish their abilities on said regions, we can achieve overall better performance. So that's the key idea. However, until not very long ago, it's an idea that was very theoretical. So there was discussion about these issues of regions of the feature space where the human might be better, where the model might be better, mathematical proofs about how a function will converge faster or slower to the ideal solution, but a lot of real-world problems were being completely neglected. So one of these is the fact that most of these algorithms, to ensure their theoretical guarantees, require us to have a set of instances to train both the machine learning model and the assigner that's going to predict each human's decision on each instance. We would have to have not only a label, but also the decision of every expert for every instance. So as you can imagine, if we're doing this, let's say, for a bank, we would have to take the 50 analysts in a team and get them to label thousands of instances just to train this model, which would become prohibitively expensive. So the way this problem was solved so far in literature was not very good, which was we simulated human experts, but in kind of simplistic ways, as I'm going to show a bit later. Then the other limitation that was ignored is that human work capacity cannot be assumed to be as large as the models. So let's say that we have an expert that's consistently more accurate than the model and all other experts in the entirety of the feature space. These systems would spit out that the optimal solution would be to just give all of the cases to that expert, which is not ideal. And not only that, even if we set some sort of regularization parameter that says, okay, the model can decide on 80% of the instances and the humans only on 20, we have no guarantee that that's what we're going to have at inference time. Maybe one day, 3 or 4 people are on paid time off, and then your system doesn't work. And that's also an issue. So the deferral needs to be taking into account the human work capacity at inference time. And then the final issue is just that another thing that's not considered is that we don't always want to maximize accuracy. So unfortunately, most works use datasets such as image identification datasets, sorting images into like which animal is on the image, and their accuracy is a fair metric. But if you're talking about medicine or fraud, you might want to prevent the most false negatives. Let's see, if we're talking about cancer screening, for example, it's less unpleasant to scare someone with a false positive than it is to send someone home who was in fact ill. And in banking, we might even want to have instance-specific costs. For example, if we fail to detect fraud on a transaction, the cost we're incurring is the value of money that's going to be lost associated with that transaction. So lots of problems that I'm setting up because the thing I did is going to solve them. And there are some others that I didn't, and we'll talk about those later. But let's talk about our approach to training a deferral system under these real-world conditions. So this is training the assigner, the thing that so far was a little magic box. And for the data, instead of assuming we're going to create a huge set of expert decisions just for this use case, we want to assume that we have a history of past expert decisions. So let's say we're working in banking. We are going to have the list of previous decisions on whether a transaction was fraudulent or not. And of course, each instance only has one associated decision. So let's say expert J said this is probably fraud and declined the transaction or blocked the card or whatever. But we didn't actually take all of the expert team just to look at one instance. It was a single expert. So essentially what we're going to have is, instead of the ideal scenario where we have for each instance characterized by a vector of features and a label, instead of having all of the expert decisions, we are going to have only the decision of one. So this means we can use past decisions to train our system instead of having to start a new collection process all over again. This is what makes the application of this system feasible in real life applications. Otherwise, it would be too expensive. So you are seeing some math here, but it's not that scary. Unlike many previous works, which try to train everything together, so the model and the deferral to a human all together, we assume that the classifier has to be a separate component. Why? Exactly because of the problem that we are talking about. On inference, we might have to defer either more or less to actual humans. So we want a classifier that's okay on the entirety of the feature space and not let it specialize too much to places where it assumes we are not going to be deferring to humans, which would be the result of using like composite loss function. So this that you're seeing here is just a weighted logistic loss. If there are first year students of the data science masters, they will like this one a lot. But we add a little weighting term with the relative cost of the instance. So the cost is given not by an empirical quantity like the value of the transaction, because we are going to apply this to bank account opening applications. So there's no way to really know what the loss is going to be in a scenario like that. But through working with several clients, we have seen that usually what banks do is consider that a false positive, so allowing someone to open an account that they're just going to like spend all the credit and then not pay and default on those debts, is about 20 times larger than the cost of declining a legitimate customer. So that's what we're assuming. And this has several theoretical guarantees that tell us that the estimate of the probability is going to be calibrated to this cost scheme. So if it gives you over 0.5, it doesn't mean that the likelihood of it being false is larger than 0.5. It just means that it's more likely to incur less cost to signal fraud than to not signal fraud. And then we do something very similar to train the human expertise model. So what is this model? The idea here is that we want to predict how likely a human is to be correct so that we can decide whether to pass a given instance to the classifier that we just trained or to a human in the system. So the way we chose to do this was to just add the expert identifier as one of the features and train a single model to model all of the experts. Now, why is that? Usually, experts have certain ways they arrive at their decisions. They are not fully predictable. They are not fully modelable, but they are going to agree more than not. So by creating a single model with all of the expert predictions, allowing for the feature of the expert identifier to sway the model a little bit, we are essentially modeling the overall expertise of the team, but allowing for specialization if, for example, one of the experts is just extremely more likely to be correct than the others. This is essentially very similar to the logistic loss, except that instead of penalizing based on whether or not the label concurs with a prediction, we are penalizing based on whether or not the expert prediction matches the label. So whether the expert is correct or not. Then, because of mathematics, which don't require being explained for the purposes of this presentation, this also gives you the same scaled function that we were talking before, that is larger than 0.5 if it's beneficial to pass the instance onto expert J, depending of which J you plug into the model. Now, of course, the idea is to maximize this measure, which is connected to the likelihood of the agent making the decision, be it a machine learning model or an expert, being correct. So we're not actually maximizing that likelihood because it's cost sensitive, so it doesn't track one-to-one, but we're maximizing this quantity, which is kind of like a utility, a benefit of deferring the instance. So the algorithm has three separate parts. The two first ones are the ones we just described. And then the idea is that by taking the probability of the model being correct, which is given by its own model score, and the probabilities of each expert being correct, we have an assigner that will essentially maximize this probability of being correct by picking which instance is going to be assigned to each human. And it's on component 3 that we have to introduce some sort of constraint programming to find the best set of assignments under our constraints. This can be done, for example, in batches of days. Let's say for a given day, we have a queue of alerts that need to be reviewed by financial analysts, and we employ the algorithm at the beginning of the day, and then each of the instances is forwarded to the experts to do their regular workday. So our assigner has a complicated task, which is to decide on an assignment decision. So that's kind of redundant, but essentially this means that we either give it to the machine learning model because we know it's going to predict the negative class. We know this beforehand. We don't know what the human is going to predict. We either pass the decision to the model because we know it's going to predict the positive class, or we pass the decision to one of our J experts because we think it's more likely to be correct than the model. So we use our previously trained functions to estimate the negative class, which is just 1 minus the score and the score for the positive class. And then we, for each expert J, get our model output for a given instance to obtain the likelihood that the expert will be correct. So if you imagine a nice matrix with all of these probabilities, what we essentially want is to multiply it element-wise by another matrix that will just pick, if left unconstrained, the highest value of each row, right? So if we could just give all of the instances to the best decider, we wouldn't need a matrix. We would just take an instance and give it immediately to the person with the highest score or to the model. But since we're talking about doing, for example, this batch for an entire day, we would want to obtain the optimal matrix A that maximizes the selected probabilities of correctness. Of course, this has to be subject to some constraints, and this is a bit hard to read, but essentially what this means is we can only select each expert a given number of times. So for example, 10. Let's say an expert can only solve 10 cases through the course of a workday. And we also need to ensure that each decision only goes to one agent. So it either goes to the model or to one expert. We're not allowing the matrix to say you should send this to 2 experts and average their decisions or something like that. So essentially it's one per row of the matrix, and the sum of the columns for the experts needs to not be above their capacity. So how do we test if this works? Now, this is a key problem in learning to defer because, as you can imagine, if you're actually going to test whether this system functions or not, you would have to have the 50 experts on standby to defer all the instances to them, have them decide, and then get your results. And then if you decide that you wanted to like change a hyperparameter, you would have to do this all over again just for testing. So that's why we actually have to use synthetic human decisions. And we're going to simulate essentially what happens in most financial institutions when it comes to human review of transactions, for example, or bank account opening applications or loan applications, which is out of all the applications, there is going to be a model that has nothing to do with this. It's a predefined model that will just select which ones are the high risk. The low risk ones are automatically accepted because just the cost of doing the process for all of these low risk ones is lower than the few errors that pass. And then on these high risk instances is where we're actually going to apply our decision system. So essentially, these are a bunch of financial experts receiving instances that for one reason or another, let's say rules or a previous machine learning model are considered risky, and it's on those ones that we're going to apply our learning to defer approach. So to simulate the human expert decisions, something that the initial works did was to take, as I told you, this data set of selecting images, and they would simulate experts by saying, okay, the expert is going to be completely correct on these first 5 classes and predict at random on the second 5 classes. Now, that isn't really how humans work. I don't think there are a lot of people who could always tell that this is a cat, but all of a sudden, if it's a dog, they're completely clueless. So we need to simulate something a bit more complex than this. Why? Because if you take the models that actually predict which class the images belong to, they all have extremely high accuracies, 95 plus, and this has been happening since 2017 with the first CNNs, and these are essentially just the ROC curves for dogs, birds, cats, etc., for each of the models. But the point of this image isn't to really analyze it too much. It's just to show that these models are perfect, almost, at capturing which class an image belongs to. So if our human behavior is just based on which class the image belongs to, we are essentially just giving the model the answer. We are giving the assigner the answer. So the assigner will very easily detect that experts are always correct here and are correct half of the time here, because they can differentiate the classes very well. So in reality, the curves you get when you try to predict a human decision, this was done on actual financial fraud analysts, are much more modest. So they are much less predictable, not only because you tend to have less instances to train your model on, but also because humans are unpredictable in their decision making. There are hidden factors also that aren't fully captured by the features, and so on. So our humans need to be a bit less predictable. So what we did was basically just simulate kind of a logistic regression as how humans decide. So instead of fitting a logistic regression to real human decisions, you can just decide on the parameters yourself if you want to simulate the hypothetical human that is affected by each feature differently. And instead of simulating which decision the human is going to take, because predicting a logistic regression would also be very easy, we simulate the probability that the human will make a mistake on that instance. So the idea is that each human will have different patterns of decision making and will be making more mistakes on different regions of the feature space. So the model actually has to learn where experts are more likely to make mistakes and distribute the deferrals accordingly. So we allow, for example, to set the base probability that someone will make a false positive error or a false negative error. You can imagine this as a more cautious and a less cautious analyst, so someone who is less worried that something could be fraud versus one that isn't. This is also something we see in real life. And with a little alpha parameter, we're just calculating how much the expert is swayed by the features of an instance. So if you imagine alpha equal to 0, it would be someone that guesses at random with a fixed probability of error. And if alpha is very large, it means that there are going to be instances where the expert is almost completely wrong, and others where almost completely always right. So by tweaking these, we get some curves that are much more similar to the human ones, while still being a bit more predictable because we just have more data in this synthetically generated scenario. But this use of logistic regressions to simulate human error is something that's actually still done in medicine. They don't like machine learning a lot in medicine. But so we chose it to simulate our experts. So that's how we got it to be as realistic as possible. So let's compare this to another method. So our method tries to maximize the probability of being correct globally, and to our knowledge, no method before was doing that. But there is one other method, which is by the author cited here, which tries to simulate each expert with binary classifiers, so not a single expert model for everyone. Does more or less the same we do for the classifier, and then just passes it on to whoever has the highest score. So the deferral is done in a greedy fashion. So let's say if there is an expert 2 who is better than all of the other experts, that expert's going to get the first 10, and then that expert is spent. We are going to have to choose someone else. It's not optimal. So basically, we also change a lot of different things. We assume that we can have different ratios between the cost of missing a label positive instance and a label negative instance. We assume that instead of the experts getting the 5% more risky instances, they can get the top 15. And essentially, we vary the capacity of each expert randomly across a bunch of scenarios just to allow us to get error bars on our results to make sure it wasn't just because we chose the number 10 that our model is better than another. So if we look at the expected calibration error for our classifier, it's pretty good. We can tell that everything is very well calibrated. That's what we want for our system to work. So if something goes wrong later, we can be sure it isn't the classifier's fault. So this is the classifier that's going to be used for both deferral methods. So we can now see the results based on the merits of the human correctness models themselves. So we have the approach, ours, that uses a single model, and the other one that used one model per expert. And if we compare them, they actually perform pretty similarly when it comes to the ROC curve area. So you can see that they're always within their respective error bars. But for some reason, it seems that depending on the ratio between the cost of a false positive instance and a false negative instance, the calibration is actually much better for our model. Now, why is that? It's essentially because of what I was saying before. We have the advantage in a limited data scenario of kind of pooling all of the expert predictions together, because we know that they're going to be at least somewhat similar. While the other models are essentially just simulating the probability for each individual in a vacuum. And then if we just look at the total cost incurred by the deferral, the numbers really don't mean anything. It's 1 for failing a false negative, and 1/20 for a false positive. And essentially, this is just to say that our method did better. So you can ignore all the numbers. You just look at the bolded line. It's all under our method, and that's what matters. So, so yeah, but these have a lot of like specific parameters that we can get into in the questions, I think. So essentially, if we just look at the cost incurred um, per each 100 instances, and we vary the amount of training data we have for each model, we can see that ours performs better in all scenarios, essentially. Even when using just 25% of the data, we get a better result. That makes sense because if you're training each expert classifier individually and you have, let's say, 20 experts, you're going to be training classifiers with a 20th of the data instead of training one big pooled model with all the data. That's essentially the main difference between the two methods, and we confirmed that it does pretty well because of that. And well, essentially that's it. It's we propose a constraint-aware learning to defer method. So because of that matrix deferral system, we also take into account the fact that usually we won't have a huge pool of expert predictions to train our models on. We get statistically significant better results because we are jointly modeling the expert team. And in future work, ideally, we would be able to take our current losses and add some sort of fairness regularization term, which would allow us, for example, to ensure that false positive rates are the same across, let's say, men and women on financial loan applications, so that the system is not only accurate, but it's also fair. We aren't having worse performance on social subgroups within the data. And I think that's all. I don't know how we're doing on time. Is that... Thank you. I wanted to leave a lot of time for questions because I assume there are going to be some. So
The comments, maybe you can mention that there are two papers that are all good.
yeah, there are. So we have a paper called, for these results here, we have a paper called Learning to Defer Under Cost and Capacity Constraints. And for our method of simulating humans, we actually refined this and used real data from cardiology studies on the consistency of human decision making, psychology studies, studies on how likely ophthalmologists are to predict correctly or wrongly on the same image. Even software engineers estimating how long it will take to fix something is something that varies a lot. Probably some of you guys can relate to that. And the data set we generated with a slightly more refined version of this approach was published on Nature Scientific Data column. It's not really a column, it's a journal, a sub-journal of Nature, which is called the Benchmarking Framework for Learning to Defer. And yeah, those are the two that came from this work, essentially. So questions?
So if we know the data beforehand, I was wondering, what's the feasibility of casting and killing experts as we go, according to the data we're getting?
Sorry, if we know the data beforehand?
Yes, that we need to classify. I was wondering what's the feasibility of casting more experts, depending on the topic that we see that is going to be to be evaluated, or killing them if we don't need them.
Yeah. So I don't think, I think you can fire them. You don't need to kill them. And getting more experts is something that I'm not sure any work deals with so far. So the problem of getting newer experts in on the model that you already have is that you don't know how they behave. So you can just plug in a new expert to the model we already have to add them to the system. Also, you won't have an history of decisions for that expert to train the model on. There is one work that what they do is essentially they have a model they already have. They pretend, okay, a new expert arrives. They make that expert do a small test of predictions and then add them to the model. And they show that they get decent results with 100 predictions, which essentially means that if you want to add someone new to the system, you would have to sit them down, make them take a test, and then retrain your model to add them to the system.
I have a question as well. So you mentioned that we may have cases where one agent is really good and has almost 100% accuracy. So I was wondering if we might have a risk feature an importance or risk feature associated with each transaction in your case, so that in those cases we might choose the really good one, even though that person might be overloaded with tasks.
Yep.
And at the same time, we might have metrics associated with overloading a certain person. So I was wondering if there is research on that.
I think so. So the way we take into account how risky a feature is to get a mistake on ends up being included in our probability estimate itself, because we are training the model with the cost of each error. So let's say we have an instance that's a transfer of $20,000 to someone. It's going to weigh 20,000 more than a $1 transfer.
Okay.
So depending on which expert is better on that instance, that deferral is going to be considered more important. Now, if what you mean is at inference time, tweaking the cost itself, we might want to have it as a feature of the model. What's the issue there? We run the risk of training a system that ignores the small value transactions to catch the high value ones. And it would end up being discriminatory because the accounts that would benefit more from the deferral system would be the richer people.
But we might have a regularization parameter to make sure we don't do it.
And that unfortunately, if we add those sorts of regularization terms to the loss, it kind of throws off the calibration of the probability estimate. But it's something that some people are working on. But I haven't seen any works that put all of it together. But ideally we would have a regularization term.
Okay. And something that also can measure how much we are overloading a person. If that person is really good.
I mean, for that case, ideally, we are just setting in the assigner constraints how many cases can go, let's say, per day, per hour, to a given analyst. Now, what might happen if you have an expert that's better than everyone else is that guy is going to get the harder ones all the time. And what's the problem with that? If you have a system where you defer randomly and you want to evaluate who's your best expert, you can just check who gets the most right. But if now you have a system where the best expert is getting all the hard ones and the worst expert is getting all the easy ones, how are you going to evaluate their work performance? That's also, you get into a lot of moral dilemmas when you talk about applying this for real people. But when it comes to just workload overload, you can define it in the constraints at inference time. So if someone took the afternoon off, you can cut the the number of deferrals that are allowed for that person for that day by half.
Okay. Okay, makes sense. Thank you.
Thank you.
Any other questions? Okay, I think that's it. Thanks a lot.
Thanks very much.
Yeah.